Yeah, thank you.
So, okay, thank you for having me here once more. And well, also I would like to apologize because these days I haven't given my full attention to the workshop because I had to take care of some teaching issues. So I apologize for that. But still, really nice ideas, everything that I have seen so far, and I am glad to be here. So yeah, I'm going to talk about Finsler geometry, and I also apologize because this is going to be a bit more of a technical talk than the one that I gave last year. Actually, what I'm going to do here is to do a review of how is the field nowadays in what it comes to take Finsler geometry and use it to generalize general relativity. So for that, well, I also refer you to my talk of previous year, which was a bit more elementary, and you can see it also in the YouTube channel. So I hope that with this reference in mind, there won't be much issue, but I will try to give as much intuition as possible. So yeah, also I want to focus on this occasion on some other types of problems which are different than what I told the other time, but that they also justify or motivate, try to use Finsler geometry to describe the universe. And then after these other problems, I will go about more into detail about what people have done, mainly to generalize the Einstein equation to this new Finsler geometry. So in some sense, I would be generalizing what Dishant talked about this morning. And yeah, in the point number 3, I will tell you about a bit about what I did in my PhD thesis, but I will try not to be too technical there. So, okay, about motivations for Finsler geometry. Well, here in this one, I will go a bit faster because this I spoke about the other time. I posed the question of what's the probably most fundamental problem now open in fundamental physics. Well, arguably, it's to unify quantum physics with general relativity, which, as one knows, describes the geometry of space-time. So in one sense, one is looking for some quantum space-time geometry, and of course, we do not know the full theory for that, but people in physics try to give, okay, we don't have the full theory, but they try to give predictions. So they do quantum gravity phenomenology. So it's like you take the classical geometry and you somehow want to deform it to give predictions that are according to quantum theory. To be a bit more specific, they do this with modified first-person relations. This is relatively easy to understand because in space-time classically, one has particles with mass, energy, and momentum, and there is this classical relation between mass, energy, and momentum, which is known as the dispersion relation. But now in this quantum geometry, what one wants to do is to take this and deform it to a new type of relation, okay? So there appears some function h, and if one wants to understand this in geometric terms, well, first, classical case. In the classical case, what is happening is that space-time is carrying a Lorentzian metric, which is the one that Dishant told you about this morning, and then this classical left-hand side in blue is just the metric applied to the form momentum of the particle. But now we want some deformation given by some function. And how to understand this in geometric terms? Well, we will switch from the cotangent bundle to the tangent bundle, okay, to make things more intuitive. So the tangent bundle, it's just the collection of not only points, but also all possible directions or velocities on space-time, and we will work there. And then, well, in the classical case, one had the metric on velocities, but now what we have is some function, L, okay? Because people figured out that you can do a procedure to move from the cotangent to the tangent bundle, and one has this function, L, which is supposed to describe all my geometry of my spacetime, okay? Important thing is that this function L is homogeneous of degree 2 with respect to the velocities, but well, one can also work with a homogeneous function of degree 1 instead of 2. You just take the square root and you work with a function of degree 1, if you want, on the variable x dot, okay? So this type of things is what I refer to as Lorentz-Finsler metrics, okay? Because they are generalizing by a lot. They are generalizing the classical Lorentzian metrics. and they give you your space-time geometry. In particular, for example, now the geodesics of this new metric, so the straight lines to quote-unquote straight lines, will describe the free-falling particles. But okay, now let's get a bit more specific about other motivations, because the other time I also talked something about quantum gravity, but I didn't give many other motivations. Well, what I want to point out today is that this Finsler geometry in space-time is a very active field of research nowadays, because actually it arises in a variety of settings, okay? So for example, these Lorentz-Finsler metrics arise in other models of physics. To cite some, let us cite the very special relativity model by Cohen and Glashow, as in the Nobel Prize. Well, but this very special relativity model, what does is to take the classical Lorentzian geometry or Lorentz symmetry of space-time and to realize that you don't really need that much symmetry to describe, like, basically, or to be consistent with the known physics. So one reduces the symmetry and one obtains a model which is called very special relativity. It's a very important model. Also, for example, if one wants to take the standard model of particle physics and one wants to extend this model because one, for whatever reason, doesn't believe that this classical symmetry is fundamental, one extends it. And when one extends it, one obtains the so-called standard model extension, okay, which was obtained by Edwards and Kostelevsky. And this one is also an example of Lorentz-Finsler geometry. So basically, one takes the main theories of modern physics, and when one wants to generalize this model for new geometries, one usually ends up with this Lorentz-Finsler geometry. And I want to say that this is one of the main motivations to study this field nowadays. But also, from now a bit of a more mathematical viewpoint, let's say. Well, it turns out that when we study space-time, well, what are we studying? We're studying how observers measure time, how observers measure distances. But one should think that in these postulates of how people measure time or people measure distances, there are usually some like hidden assumptions. There are some hidden assumptions of linearization, let's say. There are some simplifications, okay? At least from the mathematical viewpoint. And when one takes these simplifications and one undoes them, one also ends up in the framework of Lorentz-Finsler geometry, as was shown in this paper by Miguel Ángel Jabaloyes and Miguel Sánchez, my thesis advisors, together with Bernal. So this is also a mathematical motivation to study Lorentz-Finsler geometry, which is, let's try not to make simplifications about how measurements are made in space-time. And yeah, this also leads to Lorentz-Finsler geometry. There are also some axiomatics for space-time, such as the famous Ehlers-Piranian-Scheil one. And if one takes this type of axiomatics and one really takes them like seriously philosophically and one analyzes them, if you analyze them, then you realize that actually the Lorentz-Finsler geometry is also allowed by this type of axiomatics. So you have to also consider it. And well, this one I also talked about the other time, but now people are taking seriously the idea of using this Lorentz-Finsler geometry like to address the main problems of general relativity, some of which, as you will probably know, are the problems of dark energy or dark matter. But let me go just a bit into details mathematically. So as I said, I will work on the tangent bundle of my space-time. So this is the space of all possible points and directions in a space-time, so points and velocities. I will use some coordinates, x mu for the position, x dot mu for the velocities. Well, this is an important notation. This notation f dot mu represents the partial derivative with respect to the vector coordinates, and this is called the vertical derivative. And well, I will work on some subset A of the tangent bundle, okay? The details are not super important, but this set A of directions in my tangent bundle will mean, from the physics viewpoint, will mean the time-like directions, okay? But let me just say that I will work there. So what is mathematically a Lorentz-Finsler metric? Well, Lorentz-Finsler metric is a certain function defined on this set A of directions. As I said before, it's homogeneous of degree 2, but one also requires that this object, called the fundamental tensor, is a non-degenerate tensor, okay? Non-degenerate tensor, and moreover, you're required to have this concrete signature to basically distinguish between time directions and space directions. That's the motivation. So this shows you that what we are doing here is a generalization of what, for example, Deschamps said this morning. And now I have some type of metric that not only depends on the point where I am in space-time, but it also depends on the direction. And this is like the main change, okay? And well, I will ask my functional to be positive because it's going to mark like the time-like directions, okay? Yeah, I mean, I understand that only by words this may sound a bit abstract and we like geometry. So what's the intuitive picture? Well, if you remember or you see my talk of last year, the message is that what we are doing here is we take the basic shapes of relativity. What are the basic shapes of relativity? Well, the basic shapes of relativity are the light cone, okay, the cone formed by all the directions of light, possible directions of light, and also the hyperbola of time-like direction. So the main moral is one takes these classical shapes and one deforms these shapes to new ones. Well, the technical requirements may vary between authors, but okay, so that's why I have included here different references, which you can see later. But to get across the main message is you take this classical shape and you deform it. So this is how you should think about Lorentz-Finsler geometry in like pictorial terms, like in something that you can visualize. And you could take, for example, the classical cone of like directions, and then you deform it, for example, in a way that it is not round anymore, okay? So for example, now if I take my cone of like directions and I cut it by a hyperplane, I do not get some ellipse anymore. In general, I will get some convex curve, which, by the way, seems to go quite well with the Sapper formula and things like that could be modeled that way, for example, okay? So just to try to link ideas. And this is the type of deformation of the geometry that we do, okay? But now for some, some formulas of some concrete examples of this type of metrics. Well, to put concrete examples, one doesn't want to deviate too much of the classical geometry, so one takes the classical Lorentzian metric. I'm going to call it alpha this time, so it's an object of this type that depends on the position and then measures velocities. And then I will also take a one form that somehow will measure my deviation from the classical geometry, okay? Well, a one form is the same as a vector field on space-time, okay? So it's something of this form, it will have certain coefficients. And with these two ingredients, I will build some concrete Lorentz-Finsler metrics, okay? That, as I said, is take the classical geometry given by alpha and then deform it, okay? These are called the alpha-beta metrics. The definition may be a bit technical, but yeah, the idea is that it's all possible metrics that you can build in this way. So as you can see here, you take the classical metric alpha, and then you do some deformation by using a function phi, which is some anisotropic factor. It's a factor that depends on the direction, and well, it can be made to depend precisely on this quotient, but details, again and again, are not super important. The idea is the message is that you take the classical geometry and then you deform it in some anisotropic way, okay? Some concrete forms that the metric could take. For example, one has the Rwander's metric, which was first used to model electromagnetism in space-time. And the Rwander's metric is just you take the classical Lorentz metric, the alpha, and you deform it in this way by just adding the one form on the vector field. This is a possibility. This is the Rwander's metric, and it corresponds to this function. But of course, one can complicate things more and more to get like more varied Finsler metrics. Okay, for example, there is the Kropina metric, which corresponds to this choice of phi, and it takes this form. you can complicate things a lot. For example, to go to the Bogoslovsky metric, which is also very important in the physical models that I told you previously. And for example, it would take this form in terms of the ingredient, okay? This is just to show a couple concrete forms that this new metric, this new geometry could take, okay? What are the geometric objects? Well, the most important objects associated are the geodesics. What are the geodesics? Geodesics are, of course, like the most straight possible curves in your space-time, okay? And they are, as in classical relativity, you find them by considering the length functional, so it's the integral of the function f, and then try to minimize it, and the resulting curves will be your geodesics. Or also you take what is called the energy functional, which is just the integral of L, you try to minimize it, and you get these special paths with other geodesics, which of course are relevant because these geodesics are what models the free-falling particles in space-time, okay? Now, these free-falling particles, these geodesics, will satisfy the so-called geodesic equation, and here there appear some coefficients in this ODE. These coefficients are important. This form what is called the canonical sprite, okay? This is a type of vector field on the space A, okay? Again, not super important, but it's an important geometric object because this object, these coefficients, like dictate how your particles are going to move in a space-time. And they are going to move by solving this ODE system, which is a really important thing. And now you take these canonical coefficients, these canonical sprite coefficients, and you can use these coefficients to build different notions of covariant derivatives, but most importantly, of curvature. After all, another thing that you want to measure is the curvature of your space-time, because the curvature will affect the curves, and it will affect how particles move in space-time, okay? Well, the most important one for me is the so-called Ricci curvature, okay? It's a possible measurement of curvature, okay? And it's also defined by some function on the space A of directions, of time-like directions, eh? And classically, it would take this shape, but of course, this is the classical Lorentzian case. And in general, all that I can say is that it's some function on the set A that measures like my curvature of space-time in all possible directions. Okay, I want to do, before going in what's happening today, I'm going to do a bit of a historical revision of what has people done, because here the important thing is, okay, in Einstein's general relativity, the Einstein field equation tells you how matter affects curvature and how curvature affects matter. So we want something like the Einstein equation, but for this new Finsler geometry, okay? Now, what have people done about that? Well, this one is not very important. Let me also mention that there are some quantities that measure how your geometry, how far your geometry is from being the classical geometry. And, well, for example, there is the Berwald tensor, which is take your canonical coefficients and take a third derivative. You have something weaker, which is called the Landsberg tensor. You have something even weaker, which is called the mean Landsberg tensor, okay? This is just to show you that there are like certain quantities, certain invariants that are new in this geometry. And the important thing about these invariants is that they tell you somehow how far is your Finsler geometry from being the classical geometry, okay? So one can have different conditions where these quantities vanish, but in general, they will be different from zero, and they will enter the new equations, okay? The new equations for the curvature, these new quantities, they will enter, okay? Don't, as always, don't want to enter much into the details, but they are called the Berwald tensor, which is like the strongest thing, the Landsberg tensor, and the mean Landsberg tensor. By the way, there are some important conjectures in geometry, in Finsler geometry, purely mathematically, that tell you that if one of the quantities is zero and things are very regular, then the stronger quantity will be zero. So, for example, it's a conjecture that if the Landsberg tensor vanishes and everything is like totally regular, then the Berwald tensor will also vanish. But these are still conjectures. They are very important in the field, but they have still not been proven, okay? So because of this, all these new quantities will enter in the new equation, okay? So here it's like, I am not saying much because I am not telling you much about how these quantities are defined. It's complicated, but I just want you to realize that in the new geometry, a lot more new quantities will appear than before. These were not present before, and now we have to take care of them. So things are difficult. It's difficult to study these topics, these equations, because of this type of new objects, okay? Okay, so let us now go into the historical revision of what have people done about this. So in order to generalize the classical Einstein equation to the new setting, you could, this is what Asanov did first, you could, for example, take a privileged vector field on your spacetime. This is like, you may think about it as a field of observers, some privileged observers for some reason, and then you use them to construct an auxiliary metric, and then you formulate the classical Einstein equation. This is one possibility. This is one approach in order to do it. Of course, this has problems. Like, for example, it is not very clear what is the relation between this vector field and my true degree of freedom, which is the function L. Like, what's the relation? It's not very clear. For example, Miron did a bit of a variation of this, but something a bit similar. It's you take this fundamental tensor, you construct a new metric called Sasaki in the space A, okay? This is a classical Lorentzian metric, and you formulate the classical Einstein equation again. Okay, you can do that. And now the point is that if you do this, you obtain like this splits into a lot of equations, and now there is another issue. You have many more equations than unknowns, because remember that there is only one unknown, like only one true degree of freedom, which is the function L of position and velocity. Now, in the year 93, Professor Roots, who, by the way, I was sad to know that she passed away not too long ago. She did like the first like intrinsic equation for Finsler geometry, which was not based in anything auxiliary. And she proposed that by analogy of what happens in general relativity and Newtonian gravity, she proposed that the equation of vacuum should be just that the Ricci curvature is zero. Okay? This is a simple proposal. It totally generalizes what happens in general relativity and Newtonian gravity. Now, with this one, this is quite simple. There is just a small issue, and it's that if you directly do this, the variational formulation is lost. And one wants a variational formulation because one would like to obtain equations by saying that nature somehow tries to minimize or to optimize a quantity, okay? So we want something similar to this, but with a variational formulation, okay? But we are almost there, because if you take this simple equation and you apply it to a certain procedure called variational completion, you get to some axiom functional, okay? And just the moral of the story is like, you obtain this canonically. This is like the simplest axiom functional that you can propose. It's very closely related to the classical Einstein-Hilbert theory. And another good thing of this functional is that it leads to conservation laws. Okay, for example, from the symmetry under coordinate changes, one gets a certain conservation law that I have written here. Another good thing is that this is consistent with known physics. For example, this is almost the Liouville equation for kinetic gases, okay? So like everything leads to this type of axiom functional for your theory, okay? Now, you take the axiom functional and you get the field equation. And what will you get for your field equation? Generalizing Einstein. You will get this thing here. You will get something that in spirit is very, very similar to the Einstein equation, with just some small or not so small changes. But after all, you will get some equation that tells you that the Ricci curvature of your spacetime is related to the right-hand side, which is representing the energy and momentum that are on your spacetime, okay? For example, here there are additional terms. That's why I told you the story before of these additional objects. There appear a lot of new terms on this so-called mean Landsberg tensor that I put before, okay? I don't want to even display how the terms look like. They are very complicated, but these are the new terms that were not present in the classical geometry and now complicate things a lot, okay? Still, people try to solve the equation, and for example, one conjecture in the field is that this improved description of this, of both geometry and matter, you improve the description with respect to Einstein, and the conjecture is that this improvement and the new effects of the new terms can lead to a universe that expands in an accelerated way, okay, which is what we currently see, but you get this without introducing dark energy, okay? This is work in progress. There have already been published some solutions which do this, and I will tell you just a bit of this later. But yeah, this is like, for example, can be one of the great advantages of Finsler geometry, because you can get, for example, repeatedly expanding universe without having to introduce some mysterious dark energy. So this could be a very big advantage, okay? Now, I also want to show you, a bit of a flavor of what some exact solutions of this equation look like. So in order to make things simple, I will focus on the case of a vacuum spacetime, okay? So for now, I will not put any matter or energy distribution on my spacetime, and I will try to solve the equation in vacuum. Well, what I will try to show you is the solutions that have been published in the literature so far for this new equation with this new geometry. All the currently known solutions are reviewed in this PhD thesis, which is recent, but well, I know that I'm putting a lot of references, but you will be able to see the references later. And of course, you can always ask me about some of them if you are interested in some particular point or whatever. But okay, for example, what's the simplest solution to the classical Einstein equation? Well, it's the Minkowski metric. It's basically a special relativity, okay, which is this metric alpha here. This is the simplest solution of the classical Einstein equation. What can one do now? One can do a deformation of this most basic solution, and by deformation, one will obtain a solution for the Finsler theory. That's what we're going to do, okay? So as before, I'm going to take this vector field, the beta, okay, where I take it to be with constant coefficients, and there is, for example, a theorem that says that if I take any of these two ingredients, then whatever I do as an alpha beta metric will be a solution of my new Finsler theory, okay? So by deformation of the classical solution, you get a solution to the new theory. This is philosophically interesting, I think, because in basic general relativity, there was like one fundamental solution, the Minkowski spacetime, the flat spacetime, the spacetime with no curvature. And now what we are seeing here is that one can take this very basic flat spacetime and one has like infinitely many ways to make it Finsler, and still be a vacuum solution for your equation, okay? Because remember that the alpha beta metric, this function phi here, remember that you can choose it freely. And every time you will get a solution, okay? So I think this is philosophically interesting. What other types of solutions have people come about with? Well, for example, one can take this classical metric alpha. What is this metric? This is called the PP wave metric. But first, you take this metric to be alpha, you take the one form of this type, okay? And again, a new theorem. Whatever you form with these ingredients will be a vacuum solution for the theory. What is this? This is a PP wave. A PP wave is a gravitational wave. It's a gravitational wave of plane, a plane-fronted gravitational wave with parallel rays. So now, well, beyond details, what we are saying here is that we can take these gravitational waves known for general relativity, and now we can put them on a background which doesn't have the classical geometry. So now it's a gravitational wave propagating, but in a Finsler background, okay? One can think about it like this. So there are, with this new theory, for example, there are new possibilities for the gravitational waves, which of course will have to be either detected or not detected, these new possibilities for the gravitational waves. But at least people have come up with these theoretical solutions. Now, another weird metric, one of this type, for example. This metric is also a solution of the theory. Now, what is this? What is this metric? Well, for those who are not like totally familiar with this metric is of the type of Friedman-Lemaitre-Robinson-Walker. In other words, cosmology, okay? So this metric would be describing an universe which is of Finsler type, and it is either expanding or contracting in time, okay? So it's an universe that expands or contracts, which is cosmology, but now it's of Finsler type. And as you can see here, people have also come up with solutions to the theory which are of this type. So this phenomenon, well, as I told you earlier, really, this phenomenon of a universe that expands or contracts is also possible in this new Finsler geometry, of course, as it should be possible. Well, more of a mathematical detail, but even though the solutions that I have shown you so far look sometimes a bit weird, they still are relatively simple solutions, okay? And they are relatively simple solutions because they are of so-called Bergwald type, which, if you remember this ladder of non-classical objects, okay, this Bergwald tensor being 0 means that in this ladder, all the solutions that I have shown you so far are like in the closest type to the classical geometry still. So, of course, things can be complicated even a lot more. And now, do we have more solutions? Well, yes. For example, there is an even weirder matrix now here. This one, I won't even try to get into the details of how it looks like. Let me also mention that at the very least, it has also some interpretation of cosmology. So again, this would describe some type of universe, of Finsler universe that expands or contracts with time. Now, the interesting thing about this metric is that this one is one step further in the ladder, okay? In the sense that this one represents one step more of deviation from the classical geometry, concretely. This is what is called a unicorn metric, which means that it is of Landsberg type, but not of Bergwald type, okay? This is technical, but the moral of the story is that we try to get solutions that are further and further from the classical geometry, because we want to understand what are all the possibilities. That's what we want to understand. So, of course, it's in this sense, it's interesting to have solutions that deviate from the classical geometry of Einstein, okay? But thing is, so far, these are essentially, these are all the solutions that are known for the vacuum equation of the Finsler theory. So, of course, still things are work in progress to try to get new solutions, to see how much they deviate from the classical geometry, to see what phenomena we get in these solutions, if we get accelerated expansion, if we can describe, I don't know, for example, black holes or stuff like that in the new theory. These are things that still are remaining to be seen. So that's work in progress. Now, just in the last part of my talk, I will try to be brief, but I will comment a bit of what I did in my PhD thesis, okay? Because now I try to get across again and again the point that things are very difficult, because in this new geometry, you have a lot of quantities, a lot of new objects that did not appear before, and this complicates things a lot, okay? So what we tried to do in my thesis was to make an approach as simpler as possible to see if it has some advantages at least, okay? Try to get things more simpler, okay? So in the thesis, we start with the geodesics, but now we do not necessarily consider the canonical coefficients. We just consider some set of geodesics, let's say, okay? These coefficients are called a spray. Now it's not the canonical spray, but it's just some spray. We will start with this. There is also the notion of a nonlinear connection, which are now coefficients with two indices, and these are objects that allow one to take covariant derivatives of vector fields. And we start with these objects, but we, in principle, leave them free. We leave them independent, because we, in the end, will want to make things as easy as possible. And, well, the story that comes now is that, okay, we have an sprite that is not necessarily the canonical one. We have a connection that we may or may not obtain from the sprite. This is a possibility, but there are more. Now, what's the point of all this? The point is that whatever object you specify, you will have a notion of Ricci curvature again, okay? The difference is that now the Ricci curvature is like something independent. It does not necessarily come from the function L, okay? But rather it's something more independent. So we try to formulate a simpler theory, okay? So, well, I will skip these details, but the point is that in classical general relativity, in Einstein's theory, this was known before. This was the Palatini approach, okay? And the Palatini approach in classical general relativity, well, it says that in this classical case, if you take these objects which give you the curvature, if you take to be independent, you get essentially the same theory, okay? That's the classical case. But now in Finsler geometry, one does not know if this is true as well. So the hope is, let's take these curvature objects to be independent of the function L, okay? And let's see if we get a simpler theory, okay? So that's the idea. We take the function L, which is the metric, but we also take the connection, which are the coefficients n, and they are independent, okay? In the hopes of getting something maybe even better. We extremize the functional, we get equations of motion. For example, we get this first equation, and notice that, for example, this looks nice because this equation is the same as the one before, but these complicated Landsberg tensor terms or whatever that were present before, now they are not present. So this equation looks simpler, okay? On the other hand, we have another equation for the difference between the two possible sprites or the two possible connections. So that one we also have to study. But this is a theory which may have some advantages, okay? Yeah, mainly, as I said, these complicated Landsberg terms, they are not there anymore. Now, what's the counterpart? That, okay, the equation looks simpler, but this Ricci curvature, now you need to try and of the canonical coefficient, because remember that now it's a different one, and we have to relate things, okay, in order to make the comparison. Well, I will finish with this. The point is that we got like nice results. Well, first, some results telling us that this theory is really different theory from the one considered before. We have nice results, and I will tell you about them, but again, this theory is also a bit of work in progress, as everything, because the point is that we could not really find exact solutions for this connection thing. It was not possible for us to find exact solutions by hand, okay? Well, besides in trivial cases. So that's what leaves things still as work in progress, but there are nice results. So for example, we theoretically, with a theorem, know that if we fix the metric L, this connection will be independent, will be unique, sorry. So it's fully determined, which is nice. We have even nicer results because we have another theorem that tells us that our equation simplifies even further. And in some sense, we recover this simple equation by roots. The one that I told you before, that Ricci equals 0, we recover it because we show with a theorem that our equation simplifies a lot. Simplifies to the point that the vacuum equation is just Ricci curvature equals 0. That's the equation that we obtain in the end, okay? So that's basically like the best result. Now, why did I say that this is still work in progress? Well, because it is true that we get a very, very simple equation, but again, one has to take this Ricci curvature, which was independent, and now try to understand this Ricci curvature in terms of the function L. This is the missing step, and that's the step that we are still somehow working on it, which leaves things a bit stopped, but this seems like a good candidate to obtain a very, very simple theory of space-time geometry in Finsler geometry. We get a very simple equation, and if we really manage to understand this Ricci curvature, we will have a very simple theory to explore the new phenomena that Finsler geometry permits for space-time, okay? So this is the last step that we hopefully should be able to do in some time. I don't know exactly when, of course, but let's hope. So, well, I will leave things here with the references. I realize that there are a lot of them, so I put them so at least if you view the talk in the YouTube video, you can pause it if you are interested in some particular point. And this is everything, and let's see what the future brings. So again, thank you for having me here, and of course, any questions are welcome.
So thank you very much, Fidel, for this very nice talk. So of course there's still a lot to be done, and that's good. Huh? So anyway, 2 remarks from my side before we say. So you mentioned Solange Rutz, and she actually in 2017 she put her thesis in a booklet. So if you're interested, I can give you the coordinates. Also, this Finsler package of hers is in that booklet. So that's her thesis from 1993 plus one other paper. The second thing is that Professor Zera Ozdemir this morning talked about quaternions and so on, but they also published a paper in the hyperbolic case. With superquadric space-like and time-like vectors and all that. So I'll forward this to you and put her in CC. I don't know if she's still on the call. Yes, she is. Maybe you would like to comment, Zera, or someone else? Well, any other questions for Fidel? No. Okay, so then we've come to the end of this International Symposium, the 4th edition. It's growing every year. It's becoming more and more interesting every year for me. I start to understand more things about stuff and so on. So it's a learning thing, being exposed to other fields. It has been very gratifying for me, and I also hope for all the participants too. So I have recorded everything, I hope. I will slice it up into different talks and put it on our YouTube channel. And what I also intend to do is after or during Christmas and New Year or after New Year, I will try to group a few things like geometry and so on, and then invite people for smaller workshops to encourage, let's say, collaboration and define projects where collaboration could be done. And so on. I hope you can help and fill that in and go into smaller workshops, and then we can define real collaborations